this video, we're going to do another extra example of curve sketching. So here our function is h of x, and it looks like 5x to the 2/3 over 2 minus x to the 5/3. So we need to take the derivative at some point, and you might be thinking here, do I need the quotient rule? Okay, now you don't. So remember, when one of either your top or your bottom has derivative 0, so it's just a number, it means that you can rewrite the function without needing the quotient rule. So I could write this as 5 over 2 times x to the 2/3 minus x to the 5/3. Okay, so that makes it just a constant times the power of x. Okay, these derivatives are easy to take. So, as normal, we're going to start with the domain. Okay, so are there any x values that we cannot plug in? So what we want to think of when you have rational exponents is what is the bottom denominator, is the denominator of your exponent even or odd? Because if it's odd, like it is here, okay, they're both 3, it means that we're taking a cube root. Okay, now cube roots or fifth roots, any odd root, you can take for any x value. Okay, it's the even roots where you can't plug in the negatives. So here we have full domain, which is all real numbers, or negative infinity to infinity. Okay, so the intercepts. Okay, so the y-intercept, we plug in x equals 0. So y is h of 0, which here is going to be 0. Because when I take 0 to any power, it's 0. Okay, so we get a point at 0, 0. Okay, now for the x-intercepts, we want to set the function equal to 0. Okay, so we want to know, how do we solve this? There's multiple ways. I prefer to factor, so I can take out x to the smallest power. So I'm going to have 0 equals x to the 2/3 times, so in the first term I have 5 over 2 left over, and in the second term I have some x's. So how many x's do I have left over? Well, I had 5 over 3, and I took 2 out of 3, so I want to subtract that from here. So I'm going to have 3 over 3, which is a 1. Okay, so I just have x there. And now this is easy actually to solve where these are 0. So when you have two numbers multiplying giving you 0, it means one of them has to be 0. So x to the 2/3 is 0, or 5 over 2 minus x is equal to 0. And this means that x is 0, or x is 5 over 2. Okay, so we get an extra point here. So the x equals 0, 1 we already had. Okay, but this is a new point. So it's the point 5 over 2, or 2.5, and 0. Okay, so we have a couple of points now. So the vertical asymptotes, there's going to be none, okay, or holes, because the domain is full. Okay, so no x's missing from the domain. So we can't actually have a vertical asymptote when there's full domain. For the horizontal asymptotes, there's also none. So if we take the limit as x approaches positive infinity of h of x, when you have powers of x, it's only the sort of leading power that matters. So this limit is going to be equal to the limit of negative x to the 5/3. And when x is a positive number, x to the 5/3 is going to be a positive number, positive big number. And I'm going to make a negative, so this is going to be negative infinity. And when I do x to the negative infinity, okay, this again is equal to the limit of negative x to the 5/3. Now, this part is a negative big number, because when I plug in a really big negative number and I take the cube root of it, I still get a really big negative number. And then I raise that to the power 5, which is also odd. I'm going to get a really big negative number. So I have a negative big number. This is actually going to be a positive big number. Okay, so neither of these are constants, so we don't have a horizontal asymptote, but these can help us know the end behavior of our function. Okay, I'm not going to check the symmetry here, but this function also has none of the symmetry that we look for. So I'm just going to write none. You can check if you want, just plug in or evaluate h to the h of negative x and see if you get h of x or negative h of x. You shouldn't get either. So we're done with all the pre-calculus. So now we want to be looking at the derivative. Okay, so all the stuff with the first derivative. So we start by taking the derivative. So h prime of x, so we take out the constant 5/2. And then we bring the exponent down, which is 2/3. And then it's going to be x to the 1 less. So that's going to be x to the negative 1/3. And then I subtract 5/3 x to the 2/3. Okay, now this is hard to work with, so I'm going to rewrite it. Okay, so first of all, this 2 and this 2 cancel, so this is just a 5/3. And now it's going to be x to the negative 1/3 is 1 over x to the positive 1/3 minus 5/3 x to the 2/3. Okay, now if I want to make a common denominator to put these together, I'd have to multiply the second equation by x to the 1/3 over x to the 1/3. Okay, if I do that, now I have the denominator 3 x to the 1/3. And on the first part, I'm going to have a 5. The second part, I'm going to have 5 x, because 2/3 plus 1/3 is 3/3, which is 1. Okay, so then h prime of x is equal to 0 when the top is 0. So that's when 5 minus 5x is 0, which is precisely when x equals 1. Okay, so that's a critical number. H prime of x doesn't exist when the bottom is 0, so that's 3x to the 1/3 is 0, and that's where x equals 0. So that's another critical number, because they're both in the domain. Okay, so both of these are critical numbers. So I'm going to put them on a number line. I guess I maybe have room to do that right here. Okay, so we put them on our number line. Okay, so we split at 0 and at 1. So I want to plug into the derivative any of the forms. Okay, I'm going to use the last form, but let's say I plug in -1. So I'm going to have 5 minus, oops, wow, that was big. So I'm going to have 5 minus 5 times -1 over 3, and then this is the cube root of -1. So on the top I have 5 plus 5, so 10, and on the bottom I have -3. Okay, so this is a negative number, so that means we're going to be decreasing in that interval. Something between 0 and 1, maybe I put 1 a bit far away here. Let's just move it over a bit, so I have some room for bigger than 1. So let's say I do 1/2. So this is 5 minus 5 times 1/2 over 3 times the cube root of 1/2. Okay, now 5 minus 5 over 2 is going to be 5 over 2. That's a positive number, and the bottom is also a positive number. So here we get a positive number, so we're going to be increasing. And then if I do something bigger than 1, let's say 2, now I have 5 minus 5 times 2 over 3 times the cube root of 2. Okay, which is not a nice number, but we don't actually care what the number is. 5 minus 10, that's a negative. The bottom's a positive, so this is going to be a negative, which means that we are decreasing there. So now if I classify my critical numbers, at 0, I'm going to have a relative minimum, because it goes decreasing and then increasing, and at 1, I'm going to have a relative maximum, because I'm increasing and then decreasing. Okay, we probably want the y value, so when I want x is 1, this is going to be 5 over 2 times 1 to the 2/3 minus 1 to the 5/3. So I get 5 over 2 minus 1, so that's 3 over 2. Okay, so we have 0, 0, critical point 0, 0 is a relative minimum, and critical point 1, 3 over 2 is a relative maximum. Okay, so we want to remember that when we're doing our picture, our graph. Okay, so now I want to do the second derivative. So all the stuff related to the second derivative. Okay, so that means I want to compute the second derivative. And now it's easiest to do, so we've been using this form for all of this sort of work, okay, all of this stuff. But to take the derivative, it's actually easiest to use this part. Okay, so it's going to be 5/3 x to the negative 1/3. So maybe let's just write what that is. So I'll write it in blue here so that we have it. H prime of x was 5/3 x to the negative 1/3 minus 5/3 x to the 2/3. Okay, so that's going to be the easiest one to take the derivative from. So we're going to have 5/3 times negative 1/3 x to the negative 4/3, and then minus 5/3 times 2/3 x to the negative 1/3. Okay, now again, we're going to want to rewrite this. So this is going to be negative 5 over 9 times 1 over x to the 4/3 minus 10 over 9 times 1 over x to the 1/3. Okay, so again, I want to make a common denominator here. So I'm going to multiply this second part by, so I have 9, and then I have x to the 4/3, so I need another x. So if I multiply by x over x, that should be enough. Okay, so then my denominator is going to be 9x to the 4/3 on both. So in the first part, I have negative 5. The second part, I have negative 10x. Okay, if I want this to look a bit nicer, maybe I take out the negative 5, and then I have 2x plus 1 on the top. Okay, so this is the derivative the second derivative we're going to be working with. Okay, so what I want to do is say, okay, where's the second derivative, double prime, where is it equal to 0? So that's going to be when the top is 0. Okay, so we can solve that. So that's where 2x plus 1 is 0, which means that x should be negative 1/2. Okay, so this is a possible inflection number. And then we also want to know, where does the second derivative not exist? Okay, that's when the denominator is 0. Okay, which is going to be when x is 0. Oops. Okay, so I have two possible inflection numbers. Okay, so those are what I want to put on my number line. I guess I still want to know what the derivative is that I'm plugging into. Okay, so maybe I'll do that here. Okay, so I have negative 1/2 is the first place I split, and then 0 is the second place. Okay, now I want to plug into the second derivative, so maybe I try negative 1. So that's going to be negative 5 times negative 2 plus 1 over 9 times negative 1 to the 4/3. So because of the 4/3 exponent, okay, this part is actually the cube root of x to the power 4. So because of that power 4, all of these numbers are going to be positive. So that means the denominator here is always positive. So I'm going to have a negative, and then the negative 5. And then I'm going to have a negative 2 plus 1. That's also a negative over a positive. So here I'm going to have a positive over a positive, so I get a positive, which means I'm concave up in this interval. Okay, something between negative 1/2 and 0 is maybe negative 1/4. So then I'm going to have negative 5 times, now if I put in negative 1/4, I'm going to have negative 1/2 plus 1. And on the bottom, well, it's a positive number. Okay, I don't actually care what it is. So I have a negative in the negative 5. Now negative 1/2 plus 1, that's positive 1/2. So that's a positive. So the top is negative, the bottom is positive, so this whole thing's going to be negative, so I'm going to be concave down in that interval. Okay, now I pick 1, so this is negative 5 times 2 plus 1 over positive number. So again, I have a negative times a positive over a positive. So this is also a negative, so I'm still concave down. Okay, so I only get, at negative 1/2, I have a point of inflection because it switches concavity. So I'm definitely going to want the y value there. So the y value is h of negative 1/2. So I'm using the original equation to find this. So it's going to be 5 over 2 times 1/2 to the 2/3 minus, negative 1/2 minus negative 1/2 to the 5/3. Okay, now I think, so this, if you simplify this, you should get 3 over the cube root of 4. Okay, which is approximately 1.89. Okay, so we have an inflection point of negative 1/2 and approximately 1.89. Okay, now if you want, I have a little bit of space here, so if you want the summary table, some people like to do this. So we split at negative 1/2 and 0, and at 0 and 1. So our summary table is going to split at all of those places. Okay, so negative 1/2, 0, and 1. Okay, and then you want to think, you just want to put, okay, so when I was less than 0, it was decreasing. So in both of these intervals, I'm going to be decreasing. Okay, and then it switched to increasing in this interval and then decreasing in that interval. Okay, now when I'm less than negative 1/2, I'm concave up. And then I'm concave down the rest of the time. So all of these are going to be concave down. So then the actual shape of my graph, so decreasing concave up, looks like that. Okay, decreasing concave down looks like that. Increasing concave down is like that. And decreasing concave down is like that. Okay, so those are the shapes we're working with. I'm going to start by plotting our points. So we had 0, 0. Okay, I'm going to make this, let's switch black here. So this is going to be 1, 2, because all of our numbers are pretty small. I'm going to give myself a bit more space here. So I had another y-intercept at 5 over, or x-intercept at 5 over 2, 0. So that's 2.5. Okay, I have this point at 0, 0. I had a point at 1 and 3 over 2, which is 1.5. And I have a point at negative 1/2 and about 1.89. So that's somewhere up here. Okay, now what else do I know? So we know that this point is a relative minimum. Okay, and we know that the derivative at 0 does not exist. So that tells me that this is probably going to be a sharp turn. Okay, up here at 1, we had a relative max. Okay, the derivative was 0. So that should be a smooth one. And over here, this was a point of inflection. Okay, so we switch concavities there. We also know that as we go to negative infinity, the graph goes to positive infinity. And as we go to positive infinity, the graph goes to negative infinity. So that's our end behavior. Okay, so that's where now we want to start drawing this. So from negative infinity to negative 1/2, we're decreasing and concave down, or concave up, sorry. So it's going to come down, approaching this point, like that. At this point, it switches to concave down. Okay, so this is subtle, but it's going to switch like that. See, it's concave down in that interval. This is my minimum. I now switch to increasing, but I'm still concave down. That's going to give me a sharp turn, like so. This one is a nice smooth one. It looks like it's going to be like that. So we're increasing and then concave down, and now we're decreasing. From this on, we're decreasing and we're concave down. So it's going to go through this point and then just keep decreasing, like so. Okay, so this is what our graph looks like here. Okay, so that's putting all of this together.